Hi, in our ITCS paper on fixed parameter sensitivity oracles, we are proposing a new research direction by combining ideas from two areas that were previously disjoint. The first such area is that of sensitivity oracles, where we want to maintain a graph property under edge failures. In this example, we have certain pairs of vertices and the shortest paths between them, and it might be that if some edge fails in that graph, that the distance between these vertices increase, and we want to prepare for that. Specific to sensitivity is that all edge failures arrive at once, but we know their maximum number f, which is this sensitivity. This is also the main difference to dynamic graphs, where the edge modifications arrive one by one, but are potentially unbounded in number. And to get a sensitivity oracle, we want to preprocess the graph once into a small data structure that is then queried when needed. A query is a set of at most f edges, and we get as answer the property of that graph where the specified edges fail. And classically, sensitivity oracles are researched for properties that are polynomial time computable. For example, all paired distances, the connectivity of that graph, or certain reachability questions. But of course, some graph properties are not polynomial time computable, but at least some of them are fixed parameter tractable. That means the graph comes augmented with some integer parameter k, and if we restrict our attention to graphs with that parameter, then the property is computable in time some function of that parameter times a polynomial in the graph size. So the textbook example is if we only care about a vertex cover of size at most k, then we compute it, if one exists, in time 2 to the k times linear in the graph size. So we confine the combinatorial explosion of that problem solely to the parameter. And if we fix k to a certain value, hence the name, the whole algorithm becomes linear time. And it does not matter whether we fix k to 2 or 42. And we observed that many FPT algorithms are somewhat innate fault tolerant. So for example, in this standard branching algorithm, in the same time bound, it does not only compute a single vertex cover, but all of them. From a decision point of view, this is redundant because we can just stop as soon as we find one solution. But this redundancy can also be interpreted as some kind of fault tolerance. And we propose fault tolerant sensitivity oracles to make this connection rigorous. These are data structures with sensitivity f for FPT graph properties. To make that clear, as answer of our oracle, we want the property of the graph where the specified edges fail with the same parameter k. So we keep k fixed for all queries. As preprocessing time, we want some function of f and k times some fixed polynomial that is independent of f and k. So if you so will, an FPT preprocessing time in f plus k. What we do not want is something essentially n to the f times some function of k, because we could just get this by going through all failure sets and computing the FPT property for each of them and storing the answer. So this does not give us anything about the trivial solution. And as query time, we want something that is significantly faster than computing the property from scratch. Again, we want to be better than the trivial solution of storing the whole graph and just running the FPT algorithm. But of course, this bar is highly dependent on the property and what is currently known how to compute it. The idea to transform FPT also to other areas is not entirely new. Probably closest to our work is FPT for dynamic graphs, which was started by Iwata and Oka. They discussed the vertex cover and the cake path problem in a dynamic setting parameterized by the solution size, which will also be the examples in my talk. Their results were further developed by Almanich and Wasilewska-Williams, And recently, Chen et al. Transferred this also to other parameters, most notably the tree depth. They showed how to dynamically maintain an elimination forest, which is used to define tree depth. But none of these works discuss the setting where the sensitivity f is fixed. So they do it for dynamic graphs, but not in the sensitivity setting. Also, what is interesting, there is one ITCS work by Lagodzinski et al. From 2 years ago. They started out with a classical fault-tolerant problem, namely fault-tolerant reachability, and were looking for a graph class where they can get rid entirely of the dependence on the original graph size. So they ended up with update times only dependent on the sensitivity f. And they found it in so-called bounded independence number graphs, and then they took this graph class back to FPT and showed that also some parameterized problems that are usually hard on general graphs admit FPT algorithms on this special graph class. So they took inspiration from fault tolerance and took it back to FPT, so essentially the other way around. As I said, the first example problem we're discussing is that of vertex cover, where we want to know whether the graph with the specified edge failures admits a vertex cover of size at most k. With the current best algorithm, this can be computed in time 1.274 to the k plus k times n. So this is the bar we have to meet for our query time. And the first thing we showed is that some kind of kernelization also applies in the fault tolerance setting, in the sense that in polynomial time, you can compute a graph whose size only depends on k and f, such that if you fail the same edges in the original and in the equivalent graph, then one has a vertex cover of size at most k if and only if the other one has. This is already very nice because then the space consumption and the query time of all of our data structures is independent of the graph size then. But still we have to carefully trade off between space, preprocessing and query time depending on those two parameters f and k. This is something we inherit from the sensitivity oracles, where usually not one data structure is best for all settings. It really depends on whether you emphasize a small space or fast preprocessing or query time. And here we also have this two parameters f and k. And in this talk, I will make the simplifying assumption that the parameter f is smaller than k. This helps with writing down the results later. In the paper, we also have results for f larger than k. But still, I don't make any assumption on how much smaller f is compared to k, and dependent on their relative size, different solutions might be better. In our first solution, we get a space of 3 to the f plus k, so independent of the graph size, and it can be computed in time essentially proportional to its space plus the polynomial preprocessing, and has a query time of 2 to the f, so entirely independent of k. So we get rid of this k and the graph size in the query time. We obtain this, I hinted at earlier that the standard branching is in some sense fault tolerant. You can just add the this edge fails option in the branching tree and get the solution 1. This is what you want to do essentially if you only prepare for a few edges, but for a large parameter, large vertex cover of size k. But still you might take issue in an exponential dependence on f. So in our second solution, we bring the query time down to k square. There is some dependence on f hidden in there, but with the simplifying assumption that f is smaller than k, this is subsumed by k square. But it is polynomial in the parameters. But we pay for this improvement somewhere else, namely in the space and the preprocessing time, which has this k² term in the exponent, which then for a large k might be much larger than this 3 to the k, which we initially had here. We get this by combining the branch and bound technique, which is frequently used for exact exponential algorithms and therefore also for FPT, together with fault-tolerant lookup trees that then guarantees this fast preprocessing time, this fast query time in terms of k. But still, you may look for some solution that only has polynomial space, so avoiding this exponential dependency on f and k in the space. Our third solution comes in, which is a simple adaptation of what Elmanich and Wasilewska-Williams did for dynamic graphs. It has space k², so polynomial in the parameter, which might even be smaller than storing the whole graph. But it has a query time of 1.274 to the k. This is essentially running a vertex cover algorithm from scratch. We save this dependence on the graph size, but still the query time is exponential in k in order to get this small space. In our second example problem, we are discussing k-path, which is the question whether the graph with specified edge failures has a simple path of length k. Our solution works both for directed and undirected graphs. The fastest deterministic algorithm is running in time 2.554 to the k times some polynomial. And if you allow randomization, you can do it in 1.657 to the k times polynomial. This problem is a prototype essentially for all kinds of parameterized path problem, because classically in sensitivity oracles you discuss distances or shortest path. So a lot of techniques are already developed to preserve paths under edge failures. And we can use this, for example, for the k-path problem, but also for other parameterized path problems. There, unfortunately, the classical kernelization is not robust to fault tolerant. It's not fault tolerant. So we get this polynomial dependence on the graph size also in the size of the solution. In our first solution, we get space k to the f plus 1 with a randomized preprocessing of k to the f times this 1.657 to the k times polynomial. But at least we get super fast query time of f², again independent of k and of the graph size. We obtain this by using a fault-tolerant lookup tree of depth f, where each of these nodes holds a k-path. So this is essentially k to the f plus times k, which is the size of that k-path. This then allows us to bring down the query time significantly, but of course these trees are huge. So we also thought about a solution that brings down this space, and indeed we can essentially trade this k to the f factor here for some factor s, which is this beautiful expression. This is much smaller than k to the f. To give you some intuition, in the worst case for f equal to k, this is essentially 2 to the f plus k times f times logarithmic. So we really bring down the space and also the preprocessing time. But unfortunately, this S also creeps in the query time. So we pay this space reduction by significantly increasing the query time. We get this second solution by sampling S subgraphs of G, by in each one of them discarding each edge independently with probability f divided by f plus k. And then if you do the math with high probability for every failure set and k-path, if one survives, there is one subgraph where this combination happens together. This is a technique frequently used in sensitivity analysis introduced by Weyman and Euster. But yeah, the problem is that you then have to go through all the S subgraphs to find the one you're looking for. So far we showed different example problems for where we can obtain sensitivity oracles with the help of FPT. For the rest of my talk, I want to speak about the opposite direction, where parameterization can help in fault tolerant. So as an example, we have fault tolerant distance preservers. If you remember my drawing from the beginning, we now have not pairs of vertices, but a single source vertex S, and we care about the distances from S to all target vertices T. And the fault-tolerant distance preserver is then a subgraph of G such that for all target vertices T and for all at most F edge failures, we have that if you fail the same edges in the original graph and in the subgraph, the distance from S to T gets preserved. Meaning essentially that we want to sparsify the graph G while still maintaining the fault-tolerant information about the distances from S. And there are known solutions with essentially n to the 2 minus 1 divided by 2 to the f many edges. And also you cannot do much better in terms of the graph size in that there is a lower bound of n to the 2 minus 1 divided by f plus 1. So for a large number of failures, you essentially have to do with a quadratic number of edges in this fault-tolerant preservers. You cannot specify the graph by too much. But what happens if you only care about those distances that do not get disturbed by too much, in the sense that for any set of at most f failures, you at most get an additive term of k. So we only care about distances that do not get perturbed by too much, and this too much is governed by this parameter k. Then we showed that you can obtain distance preservers with some function of f and k times a linear number of edges. So indeed, especially for small values of f and k, we can significantly improve above the lower bound by relaxing the objective to only those distances that don't get disturbed by too much. And we also give an oracle that tells these two cases apart, so that reports for a given failure set and a given target vertex T, whether the distance is only increased by this additive k. And we get a solution that has space 2 to the k times k squared times n squared in preprocessing that uses fast matrix multiplication. Notably, both the space and the preprocessing time are independent of the number of failures. So you can really do this for a large number of failures if you want to. The query time does depend on f, but is at least independent of the graph size. And we obtain this solution by reducing the question of whether the fault-tolerant distance increases by at most k to some reachability question, and then applying a known reachability sensitivity oracle by Van den Brandt and Saranurak from 2019. So the main message here is that if you are willing to relax the objective and parameterize it, then you can really improve upon known lower bounds for the general problem. So to wrap up, we observed that fixed parameter tractable algorithms are often already fault tolerant or allowed to be made so with only small changes. And the sensitivity f fits natural to the parameterized setting. But still, we have to make careful trade-offs between space, preprocessing time, and query time to obtain sensible solutions. But we also think that parameterization can help relax some bottlenecks in classical fault-tolerant problems. So we hope to continue this direction further. And for some new research direction, listing open problems is essentially everything is open. But the most important things here would be to extend fixed parameter sensitivity oracles for more FPT properties and see what else we can do there. And for the existing solutions, bring down the exponential dependencies on F and K. Usually you can get rid or diminish the dependency on the graph size, that is fine. But still currently we have huge dependencies on F and K that must be improved. And lastly, it would be interesting to see more fault-tolerant problems that can benefit from parameterization, where you can relax maybe the objective a bit in order to sidestep known lower bounds. And with these words, I thank you for your attention.